Pell's equation is any Diophantine equation of the form Rn is a given positive non-square integer and integer solutions are sought for x and y in Cartesian coordinates. The equation has the form of a hyperbola. Solutions occur wherever the curve passes through a point whose x and y coordinates are both integers, such as the trivial solution with x equals 1 and y equals 0. Joseph Louis Lagrange proved that, as long as n is not a perfect square, Pell's equation has infinitely many distinct integer solutions. These solutions may be used to accurately approximate the square root of n by rational numbers of the form x, y. This equation was first studied extensively in India, starting with Brahmagupta, who developed the Chakravala method to solve Pell's equation and other quadratic indeterminate equations in his Brahma-Sfuta Siddhanta in 628. About 1,000 years before Pell's time, his Brahma-Sfuta Siddhanta was translated into Arabic in 773 and was subsequently translated into Latin in 1126. Bhaskara II in the 12th century and Narayana Pandit in the 14th century both found general solutions to Pell's equation and other quadratic, indeterminate equations. Solutions to specific examples of the Pell equation, such as the Pell numbers arising from the equation with n equals 2, had been known for much longer, since the time of Pythagoras in Greece and to a similar date in India. The name of Pell's equation arose from Leonhard Euler's mistakenly attributing Lord Brounker's solution of the equation to John Pell. For a more detailed discussion of much of the material here, see Lenstra and Barbeau. History. As early as 400 BC in India and Greece, mathematicians studied the numbers arising from the n equals 2 case of Pell's equation, and from the closely related equation because of the connection of these equations to the square root of 2. Indeed, if x and y are positive integers satisfying this equation, then x, y is an approximation of square root 2. The numbers x and y appearing in these approximations, called side and diameter numbers, were known to the Pythagoreans, and Proclus observed that in the opposite direction these numbers obeyed one of these two equations. Similarly, Baudhayana discovered that x equals 17, y equals 12 and x equals 577, y equals 408 are two solutions to the Pell equation, and that 17/12 and 577 408 are very close approximations to the square root of 2. Later, Archimedes approximated the square root of 3 by the rational number 1351 780. Although he did not explain his methods, this approximation may be obtained in the same way as a solution to Pell's equation. Archimedes' cattle problem involves solving a Pellian equation, though it is unclear whether this problem is really due to Archimedes. Around AD 250, Diophantus considered the equation where a and c are fixed numbers and x and y are the variables to be solved for. This equation is different in form from Pell's equation but equivalent to it. Diophantus solved the equation for equal to, and Al-Khariji, a 10th-century Persian mathematician, worked on similar problems to Diophantus. In Indian mathematics, Brahmagupta discovered that, using this, he was able to compose triples and that were solutions of, to generate the new triple, and not only did this give a way to generate infinitely many solutions to starting with one solution, but also, by dividing such a composition by integer or nearly integer, solutions could often be obtained. For instance, Brahmagupta composed the triple with itself to get the new triple. Dividing throughout by 64 gave the triple, which when composed with itself gave the desired integer solution. Brahmagupta solved many Pell equations with this method. In particular, he showed how to obtain solutions starting from an integer solution of for equals plus or minus 1, plus or minus 2, or plus or minus 4. The first general method for solving the Pell equation was given by Bhaskara II in 1150, extending the methods of Brahmagupta. Called the Chakravarti method, it starts by composing any triple with the trivial triple to get the triple, which can be scaled down to when is chosen so that is an integer, so are the other two numbers in the triple. Among such, the method chooses one that minimizes, and repeats the process. This method always terminates with a solution. Bhaskara used it to give the solution equals 1,766,319,049 equals 226,153,980 to the notorious equals 61 case. Several European mathematicians rediscovered how to solve Pell's equation in the 17th century, apparently unaware that it had been solved almost 1,000 years earlier in India. Fermat found how to solve the equation and in a 1657 letter issued it as a challenge to English mathematicians. In a letter to Digby, Bernard Frenicle de Bessy said that Fermat found the smallest solution for up to 150, and challenged John Wallis to solve the cases equals 151 or 313. Both Wallis and Lord Brouncker gave solutions to these problems, though Wallis suggests in a letter that the solution was due to Brouncker. Pell's connection with the equation is that he revised Thomas Brounker's translation of Johann Rahn's 1659 book Deutsche Algebra into English, with a discussion of Brounker's solution of the equation. Euler mistakenly thought that this solution was due to Pell, as a result of which he named the equation after Pell. The general theory of Pell's equation, based on continued fractions and algebraic manipulations with numbers of the form, was developed by Lagrange in 1766 to 1769. Solutions. Fundamental solution via continued fractions. Let denote the sequence of convergence to the regular continued fraction for. This sequence is unique. Then the pair solving Pell's equation and minimizing x satisfies x1 equals high and y1 equals key for some I. This pair is called the fundamental solution. Thus, the fundamental solution may be found by performing the continued fraction expansion and testing each successive convergent until a solution to Pell's equation is found. As Lenstra describes, the time for finding the fundamental solution using the continued fraction method, with the aid of the Schonich-Strassen algorithm for fast integer multiplication, is within a logarithmic factor of the solution size, the number of digits in the pair. However, this is not a polynomial time algorithm because the number of digits in the solution may be as large as square root n, far larger than a polynomial in the number of digits in the input value n. Additional solutions from the fundamental solution. Once the fundamental solution is found, all remaining solutions may be calculated algebraically from expanding the right side, equating coefficients of on both sides, and equating the other terms on both sides. This yields the recurrence relations, concise representation and faster algorithms. Although writing out the fundamental solution as a pair of binary numbers may require a large number of bits, it may in many cases be represented more compactly in the form using much smaller coefficients psi, bi, and ci. For instance, Archimedes' cattle problem may be solved using a Pell equation, the fundamental solution of which has 206,545 digits. If written out explicitly, the value is 776,27,140,648, 719,455,081,800. However, instead of writing the solution as a pair of numbers, it may be written using the formula where n and only have 45 and 41 decimal digits, respectively. Alternatively, one may write even more concisely. In fact, it is equivalent to solving the Pell equation. Quantum algorithms. Hallgren showed that a quantum computer can find a product representation, as described above, for the solution to Pell's equation in polynomial time. Hallgren's algorithm, which can be interpreted as an algorithm for finding the group of units of a real quadratic number field, was extended to more general fields by Schmidt and Valmer. Example. As an example, consider the instance of Pell's equation for n equals 7, that is, the sequence of convergence for the square root of 7 therefore, the fundamental solution is formed by the pair. Applying the recurrence formula to this solution generates the infinite sequence of solutions. And A001080 in OEIS, the smallest solution can be very large. For example, the smallest solution to is, and this is the equation which Frenkel challenged Wallace to solve, values of n such that the smallest solution of is greater than the smallest solution for any smaller value of n are 1, 2, 5, 10, 13, 29, 46, 53, 61. 109,181, 277, 397, 409, 421, 541, 661, 1021, 1069, 1381, 1549, 1621, 2389, 3061, 3469, 4621, 4789, 4909, 5581, 6301, 6829, 8269, 8941, 9949, and A03319. The smallest solution of Pell equations. The following is a list of the smallest solution to with n 128. For square n, there are no solutions except, and A002349 in OEIS, or A033313 and A033317, connections. Pell's equation has connections to several other important subjects in mathematics. Algebraic number theory. Pell's equation is closely related to the theory of algebraic numbers, as the formula is the norm for the ring and for the closely related quadratic field. Thus, a pair of integers solves Pell's equation if and only if is a unit with norm 1 in Dirichlet's unit theorem, that all units of can be expressed as powers of a single fundamental unit, is an algebraic restatement of the fact that all solutions to the Pell equation can be generated from the fundamental solution. The fundamental unit can in general be found by solving a Pell-like equation, but it does not always correspond directly to the fundamental solution of Pell's equation itself, because the fundamental unit may have norm -1 rather than 1 and its coefficients may be half integers rather than integers. Chebyshev Polynomials. Dimaya mentions a connection between Pell's equation and the Chebyshev polynomials. If T and UI are the Chebyshev polynomials of the first and second kind, respectively, then these polynomials satisfy a form of Pell's equation in any polynomial ring R, x, with n equals x2 minus 1. Thus, these polynomials can be generated by the standard technique for Pell equations of taking powers of a fundamental solution. It may further be observed that, if are the solutions to any integer Pell equation, then xi equals t and y equals y1 e minus 1. Continued fractions. A general development of solutions of Pell's equation in terms of continued fractions of can be presented as the solutions x and y are approximates to the square root of n and thus are a special case of continued fraction approximations for quadratic irrationals. The relationship to the continued fractions implies that the solutions to Pell's equation form a semi-group subset of the modular group. Thus, for example, if P and Q satisfy Pell's equation, then is a matrix of unit determinant. Products of such matrices take exactly the same form, and thus all such products yield solutions to Pell's equation. This can be understood in part to arise from the fact that successive convergence of a continued fraction share the same property. If pk-1, qk-1 and pk, qk are two successive convergence of a continued fraction, then the matrix has determinant k. Stormer's theorem applies Pell equations to find pairs of consecutive smooth numbers. As part of this theory, Stormer also investigated divisibility relations among solutions to Pell's equation. In particular, he showed that each solution other than the fundamental solution has a prime factor that does not divide n. As Lenstra describes, Pell's equation can also be used to solve Archimedes' cattle problem. The negative Pell equation. The negative Pell equation is given by it has also been extensively studied. It can be solved by the same method of using continued fractions and will have solutions when the period of the continued fraction has odd length. However, we do not know which roots have odd period lengths, so we do not know when the negative Pell equation is solvable. But we can eliminate certain n since a necessary but not sufficient condition for solvability is that n is not divisible by a prime of form 4 meters plus 3. Thus, for example, x2 minus 3py2 equals minus 1 is never solvable, but x2 minus 5py2 equals minus the first of maybe, such as when p equals 13 or 17, though not when p equals 41. Numbers n for which x2 minus ny2 equals minus 1 is solvable are 1, 2, 5, 10, 13, 17, 26, 29, 37, 41, 50, 53, 58, 61, 65, 73, 74, 82, 85, 89, 97, 101, 106, 109. 113,122, 125, 130, 137, 145, 149, 157, 170, 173, 181, 185, 193, 197, 202, 218, 226, 229, 233, 241, 250. The solutions of X are listed in A130226. These on values are divisible neither by 4 nor by a prime of the form 4 meters plus 3. But these conditions are not sufficient. The counterexamples are listed in A031398. The first few such are S of 34, 146, 178, 194, 205, 221, 305, 377,386, 410, 466, 482. In fact, if and only if the period length of the continued fraction for is odd, then x2 minus ny2 equals minus 1 is solvable. Cremona and O'Donnell demonstrate that the proportion of square-free n divisible by k primes of the form 4 meters plus 1 for which the negative Pell equation is solvable is at least 40%. If it does have a solution, then it can be shown that its fundamental solution leads to the fundamental one for the positive case by squaring both sides of eq1 to get, or, since ny2 equals x2 plus 1 from eq1, then showing that fundamental solutions to the positive case are bigger than those for the negative case. Transformations. The related equation can be used to find solutions to the positive Pell equation for certain d. Legendre proved that all primes of form d equals 4 meters plus 3 solve one case of eq2, with the form 8 meters plus 3 solving the negative, and 8 meters plus 7 for the positive. Their fundamental solution then leads to the one for x2 minus dy2 equals 1. This can be shown by squaring both sides of eq2 to get, since from eq2, then, or simply showing that fundamental solutions to eq2 are smaller than eq1. For example, u2 minus 3v2 equals minus 2 is u(v) equals 1, 1, so x2 minus 3y2 equals 1 has x, y equals 2, 1. On the other hand, u2 minus 7v2 equals 2 is u(v) equals 3, 1, so x2 minus 7y2 equals 1 has x, y equals 8, 3. 2. Another related equation can also be used to find solutions to Pell equations for certain d, this time for the positive and negative case. For the following transformations, if fundamental u, v are both odd, then it leads to fundamental x, y. 1. If u2 minus dv2 equals minus 4, and x, y equals u2, v2, then x2 minus dy2 equals minus 1, x. Let d equals 13, then u, v equals 3, 1, and x, y equals 18, 5. 2. If u2 minus dv2 equals 4, and x, y equals u2, v2, then x2 minus dy2 equals 1, x. Let d equals 13, then u, v equals 11, 3, and x, y equals 649, 180. 3. If u2 minus dv2 equals minus 4, and x, y equals 2, uv2, then x2 minus dy2 equals 1, x. Let d equals 61, then u, v equals 39, 5, and x, y equals 1,766,319,049, 226,153,980. Especially for the last transformation, it can be seen how solutions to u, v are much smaller than x, y, since the latter are sextic and quintic polynomials in terms of u.